Hello, everyone. Hello, Dr. Yang. I'm Cesar Benitez, and today I'm going to present propulsion and viscous flow for the viscous flow class, and this is for 2024. So I want to talk about first what is propulsion. The propulsion is a process of generating a force to move an object forward on a specific direction. It typically involves the application of a of thrust force that overcomes the resistance forces such as drag or friction and accelerates the object. So the picture on the top, that's a engine from an aircraft, and the picture on the bottom, that's rocket propulsion. So as you can see, the thrust is going upward, and the thrust force needs to be higher than the gravity and the drag in order to move the rocket, in this case, upwards. So yeah, essentially that's the key concept of propulsion. There are different types of propulsion. First, we have the aircraft propulsion, which uses engines like jet engines or propellers to um, to move airplanes. This is a picture of an aircraft propulsion. Then we have the rocket propulsion, which uses high-speed ejection of exhaust gases to generate thrust according to Newton's third law of motion. And that's a picture of a rocket. And then we have the marine propulsion, which relies on systems like propellers or water jets to move boats and ships through the water. And lastly, we have an automotive propulsion. This involves engines, could be either combustion or electrical nowadays, to move vehicles on the land. So now that we know what is propulsion and what is the different types of propulsion that there is, uh, why is viscous flow important in propulsion? Well, viscous flow plays a critical role in the design and the analysis and optimization of propulsion system because it directly influences how fluids interact with the components of the system. It could be either air, gases, or liquids. The picture on the left, that's a rocket thrust equation. So it's really, I think, is a must for us to know the fundamentals and the concepts of fluids to know and predict the behavior of the system that we may have. So how viscous flow influences in propulsion systems? There's a lot of things, but I'm just going to mention a few, like the Bunge layer effect. So the Bunge layer leads to the formation of the Bunge layers along the surfaces of the propulsion components like wings, propellers, and nozzles. So depending where you have the air and depending your shape is the different Bunge layers that you may have. So I just put a picture of a flying airplane with their equations and how that would work. So yeah, then we have the thrust generation. It's really important. The thrust is produced by accelerating fluid. It could be either like air or exhaust gas, and the behavior of the fluid is influenced by its viscosity as well. So we need to know which fluid are we working at and their properties and how this fluid behaves, because depending on the fluid and the viscosity and many other properties, that can affect our system. So, for example, I don't know if you have nozzle nozzle flow is different to have, I don't know, air or some combustion gases. So yeah, and also can help to increase the efficiency of your system overall. And then we have the design optimization. So the material selection, um, it can go from one end from the material selection, which can impact the heat transfer or the surface wear that your materials may have, and also the all the way to the computational fluid dynamics for modeling the flow behavior. So these are new technologies that are coming out. And the picture on the bottom right, that's a CFD picture of a rocket simulation. So I think it's really cool. So talking about CFD, there's two gentlemen that perform CFD tests in marine propellers using Refresco and Procol. These are codes developed by the Maritime Research Institute of Netherlands, the Marine. So yeah, they designed what I think they just model three different propellers, and they were used in upper water configurations. So um, as you can see, those are the three um, grids, and yeah, they verified and validated the results, comparing the numerical and experimental results. So the new technologies with the basics. And today we're gonna they perform three simulations, and I'm just gonna talk about the first one because we don't have a lot of time. The E779A. So this is the domain size that they use and the boundary conditions. So yeah, the table indicates the different boundary conditions that they use for the different propellers. But today we're gonna just focus on the first one. And so yeah, they perform different tests with different grid densities, so they could see which parameter will be the best. And as you could tell, you could have told, the higher the number of cells, it's the lower the error there is. So from 1.5 million number of cells, uh, they had 3.3 and 8.79 for thrust and torque coefficient, and they did a finer grid to 16.0 million, and they managed to get down that percentage to 0.5%, which is it's really nice. So after that, after they got that parameter, they started doing their test. So you can see on this graph, that's the result for the E799A, and the lines, it's the measured, the calculated, and the bold figures are for the refresco, and the ones that are not bold are for the protocol. So as you can see, the refresco is practically there. Uh, Not for the open water efficiency though, but the rest of them, I think it's really nice. And so they got an error of a thrust efficiency and the open water efficiency of 4% and the torque efficiency of 3%. So I think it's really cool um, to use all these new technologies, but also we need to know our equations and our fundamentals for our like viscous flow and also fluid dynamics for us to be able to validate our results that are that the software is showing at us. So yeah, it's nice to have it, and we need to know our fundamentals to back up whatever results that we may get in the softwares. So yeah, I thought that was pretty cool. And yeah, that concludes my conclusion today. I mean, my presentation today. Any questions or comments? We can talk in class if I have the opportunity to present. So yeah, just some backup equations, and that's my references. But thank you so much for your time and your class and this semester, and hope to see you in class. Thanks, sir.